This lecture is probably not with the best interest of a Raman optoelectronic community. Most of my work is dedicated in developing materials typically for two applications recently during the past 10 years. They are on energy conversion by means of solar cells and energy storage by means of lithium-ion batteries and supercapacitors. And more recently, my laboratory, termed Nanostructured Renewable Energy Materials Laboratory, is planning to or stepping into flexible energy devices, realizing the need for those kind of devices from the upcoming markets. Thanks again for the organizers for this opportunity. In my university, in my laboratory, we concentrate on, as I said, three types of materials: energy conversion materials, energy storage materials, and renewable materials. The reason for positioning in this area is probably you can see things which are written in red there because of their high market value. And given we can make some innovations and can develop into sellable devices, the market share that can be attracted is quite huge. And that will help people to live in a better way. Let's have a look at the statistics first. This is a table I took from one of my recent papers published in Advanced Fiber Materials. What about the future of energy and sustainability? When you look at this table, you would find that in next 30 years' time, there are going to be over 9 billion people in the planet, mostly about nearly 2 billion people more than currently existing. And when we look into their energy consumption rate, we would see that in 50 years, that's from 2001 until 2050, or from now, in next 30 years, the energy consumption rate is going to be increased or is going to be doubled. When the energy consumption rate is going to be doubled, the energy waste, most of the energy waste currently is carbon dioxide. And the world has started seeing the adversities of carbon dioxide. You would see that carbon dioxide also, the emission rate of carbon dioxide also going to be, even if it is not double, is going to be very significantly increased in next 30 years' time. There are going to be over 30 gigatons of carbon dioxide emitted per year from the energy consumption rates. That's where probably we need to switch into more renewable energy sources like solar. I used to describe solar as the ultimate human aspirations for clean energy. I given two statistics there. And the first one, you would see that the variation of prices of silicon solar cells, silicon solar cells. During 1970s, when the silicon solar cells was first discovered, it cost about $76 per unit, per kilowatt hour of solar electricity. What is its current value now? You would be amazed to see that currently the solar PV cost is about 10 cents per unit. And that well compares with the price of fossil fuels that lie between 5 to 17 cents per unit. So we don't, if that's the case, we would be seeing an enormous amount of silicon PVs distributed throughout the planet, but it doesn't happen. I'm audible, right? Okay. So silicon PV price is falling to a great level, but why we are not seeing it in the deployment side is answered in the statistics like given the right. That's the price of batteries. The solar cells do not come alone because it is not a standalone technology. It requires the energy produced because the energy produced by the silicon solar cells, not only silicon solar cells, any solar cells are intermittent. And probably solar cell is producing electricity when we don't require it. So we need to store it somewhere. And mostly people go to store it in battery. Look at the battery price. When we can buy 1 unit of solar electricity at the cost of 10 cents per unit, to store the same amount of energy, you need about nearly 200 USD per unit. So that's a huge price. That's where now most of the research is directed towards battery, including in my laboratory. The core theme of this lecture is Electrospun flexible laboratory. Electrospinning is a process for producing materials. In particular, fiber materials or fiber clothes are shown in some figures here. Electrospinning has developed a lot because it has a history of about one century. And the technology gets momentum only after 1980 with the flourishing of nanotechnology, because electrospinning is currently the only one technology to create nanofibers of almost any material in an infinite aspect length and quite scalably. There are a lot of equipments, both laboratory units, pilot plants, and production lines available commercially. We also have laboratories electrospinners and pilot plant electrospinners in our laboratory to produce nanofiber clothes of nanofibers and clothes made of nanofibers in our laboratory. Let me give you a brief look at how do this electrospinning work. It's a very simple technique that I think many laboratories and many universities have now this technology to produce nanostructured material. Essentially, it requires 3 parts. One is a syringe needle to inject a polymeric solution, a high voltage power supply, and a collector that is grounded. So essentially this part. And when we inject the polymeric solution in it, there are certain physics there. If the force due to electric fields, because when we apply this high voltage, the polymeric solution can be charged. And the force due to that electric field, it overcomes the forces due to viscosity and surface tension. A jet initiates and it extends. On extension, there are various instabilities because a lower dense fluid is passing through a high dense fluid. Then there are plenty of instabilities out there. And because of these instabilities, the fiber jet bends and it goes through tens of meters in air, and that column length is only about 10 to 15 centimeters. And in between 10 to 15 centimeters between the syringe needle and collector. And between this fiber jet moves about tens of meters, or even sometimes even measures like kilometers. And during this passage, the solution prepared to, or the solvent prepared to prepare this, used to prepare this polymeric solution, evaporates, and we get solid fibers on a collector surface. And this is directly usable. We can take this one. This will be polymeric fibers. Not only polymers, and we can get almost any type of inorganic material also in using electrospinning in diverse morphologies. If you know a little bit of chemistry of crystal growths from saturated solutions, you can play with this technology to create a number of morphologies. We have created in our laboratory not only nanofibers, we made big cauliflower-like crystals, multi-nanotubes, and more recently we have created something like a cuboidal shaped crystals in a larger scale. And people have come up with something like rice grain, nanotubes, and nano rods assembled on a fiber using electrospinning. The way it is done is, by conventional electrospinning, you get a polymeric match. And if the this polymeric solution contains the metal precursors for forming this inorganic material, then by appropriate heat treatment, take a DSE and TGA of this polymeric fiber and heat it at that required temperature where we find that some crystals are nucleating, you would get a crystal in a fiber, or you can tailor them to any shape you want. In our laboratory, we have developed numerous types of these electrospun inorganic nanomaterials in diverse shape like fibers and cuboidal microcrystals and so on. And we have studied their properties in depth for two applications. First is solar cells, and the next is supercapacitors, energy storage by supercapacitors and batteries. And we have come up with excellent results, excellent physics. Like, it is in our laboratory, we first developed a nanomaterial that support banded stripe electron diffusion by appropriately modifying the properties of a inorganic material. And it is in our laboratory, we created a fiber that can simultaneously support high energy density and power density in a battery and a supercapacitors. And with these materials, two significant developments that we made is, one is a nano rod solar module, perovskite solar module with efficiency nearly 15%. That was in collaboration with a university in Italy. And with this, for this development, we received a gold medal for engineering excellence from INPEX USA in 2016. And in another development, using some of these nanofibers, we have developed a 6-volt 75 farad capacitor with a power density up to 5,000 watt per hour, which received a gold medal and Invention of the Year from the British Invention Show in 2015. So we have developed these devices and approached many companies with them, and they all said very exciting words, very appreciative, but they did not buy these materials or devices. Then we started looking into what is the problem with our way of thinking, development of materials for advanced applications. Why is it not working out? One is either we go and develop this industry, otherwise sell these results to an industry. But when we try to sell this research to an industry, we are not successful. Then we started looking what are our failures in these materials. We find that there are two drawbacks. One is, of course, all these materials have excellent, interesting properties, and some of them were first of that kind in the world. That's why all of that were reported in high-end journals. But to produce them, they are really expensive. So the materials are really expensive because most of them were metal-based. The second thing is that all these materials were created using a polymeric route. And if we want 1 ton of this material, we probably have to burn about 5 tons of polymer that add huge environmental load on carbon emission. So that's the case. Our properties are excellent, but these are two drawbacks. One is it is high cost, and the second is the industry cannot afford it because of its carbon emission. And that with that kind of carbon emission, the industry need to pay huge money for carbon tax, which the companies do not want to afford. So we started looking into alternative technologies. So this is what we find out. Why metal-based technologies do not support sustainability or a business promotion or new quality improvement in life. But when we look into the past, the way the civilization has occurred here, they are all related to materials. Materials are the index of human progress. Even typical milestones of human progress were related to materials like Iron Age, Stone Age, Bronze Age, Plastic Age, and so on. All these human development index were related to materials. But from now onwards, we really have to relook into it. One of the cases I shown in this the figure in the right, where you see a pond and with deeper, you would see that when the pond goes deeper and deeper, we take the groundwater level deeper and deeper. When the groundwater level goes deeper, it will not be accessible for us to drink and to do our many purposes. So we cannot mine the planet anymore for our primary materials because we are going to destabilize the planet because of many reasons. One is, as I shown before, nearly 1 billion new consumers in every 10 to 15 years time. And if we have to dig the planet for our primary material supply, we are going to destabilize it. And that's not a viable solution. And when the groundwater level goes zero, we will end up with a situation called day zero, where the panchayat or municipality is saying that we cannot supply your water anymore. Please take care of yourself. And this happened actually in Cape Town in mid-2017. They declared day zero. And recently, I read some statistics saying that 21 Indian cities will run out of groundwater by 2020. So, as I think most of these participants are Indians, you need to carefully look into the way materials can be produced. What we have done, we have started looking into the largest agricultural industrial crop in Malaysia. And everybody knows that it is oil palm plantation. Oil palm plantation is the main breadwinner of Malaysia. And when we look into some statistics, it says that if we produce 2.5 kilograms of crude palm oil, it creates 100 kilogram of biomass. Other biomass means secondary biomass. And a considerable percent of it is empty fruit bunch. Empty fruit bunch is like, it is like coconut tree. If you pluck your coconuts out, what you left with is empty fruit bunch. And for next 5 to 6% is palm kernel shell, just like your coconut shell. we find that this palm kernel shell is a good source of carbon, and it can be industrially and produced in large scales. Empty fruit bunch is a source of starch and cellulose that can also be produced in large quantities because oil palm plantation is fairly distributed in the planet, not only in Malaysia. Indonesia is the largest exporter of palm oil, and you can see palm oil in many countries in Africa, India, China, and so on. Many places are. So they have these two typical materials we look into. From PKS, we have developed activated carbon and find that activated carbon is actually some nanographic carbon containing a lot of oxygen. That's where you can see a Raman spectra here. People used to characterize carbon using Raman spectra to look into their bonding and defects. So we also did that. Those are the only purpose we go for Raman, to see the defects and bonding in carbon. And we find that this palm kernel shell carbon is nanographic, and it contains a lot of oxygen. Now we start developing into the energy storage devices. I have a lot of stories to tell. We started looking into palm kernel shell carbon in 2014, and in 6 years' time, what we have is a lithium-ion capacitor with an energy density of 126 watt-hour per kilogram. That is about 60 to 70% energy capability of a commercial lithium-ion battery, and a power density of 3.3 kilowatt per kilogram. That is 10 times higher energy density power density than lithium-ion battery. So we could develop this in 6 years' time. And when we developed this, industry started interest. A Japanese company, Noritake, has invested in this project, and they want to commercialize this technology. So that's where one of the messages I would like to give to the young generations over here. When you start developing if you are doing industrial research and your eventual aim is to make a product, be careful about your primary materials. What is the source, and how can you value add it and process it? That's one part of the story. From carbon, we did not leave the palm oil plantation just like that. And from the empty fruit bunch that I shown before, it is a good source of cellulose. We extracted cellulose from empty fruit bunch, developed them into fiber cloths, like this one, what you have seen here is a fiber cloth developed from this cellulosic fiber cloth developed from empty fruit bunch. And this fiber cloth has been used as a separator in lithium-ion battery, as a membrane in a water filtration. And one another work we did is we have added some curcumin. Curcumin is the medicinal component, one of the medicinal components found in turmeric. We added some curcumin to the cellulose to make a completely renewable based wound pressing medium, and find that when we disperse curcumin into cellulose and develop them into a fiber cloth like this one, the resulting fiber cloth, the yellowish in color here, that using which you can heal your wound much faster. So there are plenty of ways we can. These are only few examples of some resources and some applications. There are plenty of ways we can further develop them into our product. We have two patents on this work. One is one patents on cellulose from palm oil plantation. One is on the development of extraction technology. And the next is on the use of it as a separator in lithium-ion battery. And more recently, we started developing the yarns the full clothes from materials, from polymeric material, not just polymeric materials. And sometimes you know that inorganic material offers some properties far better than polymeric materials. So we cannot completely abandon it. And how can we use the minimum quantity of it, which can be recycled from the existing waste and fed back into the production and develop them into functional fabrics. Functional fabrics, yeah, it do many things that traditional fabrics cannot, including sensing, data processing, communicate, transform, generate, store energy, and even grow. And this is a definition I took from Wikipedia, is the definition given there. So along this line, textile electronics has become one of the fast growing technology with a projected market size of about 9.3 billion US dollar by 2024. In future, we will see this kind of clothes containing even that those started appearing now in different, even if it is not full-fledged, some part of it. For example, your cloth can sense your heartbeat, and you are sensing it. It can send to your mobile phone, sensing and communication devices there. So how do the fibers or the basic components of these clothes? The basic component of this cloth is yarn. How to develop them and how to functionalize them, how to preserve them into the next generation flexible devices, one of our focus recently. There are many ways yarns can be produced by electrospinning. In different ways, people have been thinking about production of yarns from electrospinning for quite some time, about 10-15 years ago. Initially, people started to spin the fibers directly onto a rotating water jet and collecting the fiber. And some advanced modified technology, spinning from different directions and getting a fiber web there, and from the fiber web draw a small a yarn and get it wind somewhere. And we recently did these two. One is one piezoelectric fabrics, and the other is one perovskite solar yarns. These two, and there we developed the aligned fibers. It's not conventional. Electrospun fibers are random, but by properly controlling the electric fields between the injector and the collector, you can align them. This is the simulated electric field along this direction. We have developed piezoelectric fibers and developed the piezoelectric clothes, which I'll be detailing in next. So there, when we develop fibers, what are the issues there? How do we characterize them? Do we need to characterize them the way we characterize other materials, like other devices like thin film or conventional materials? Do we have to consider additional characterizations or considerations when we take fibers? We have discussed enormously on this topic in this issue in Energy and Environmental Science, published last year, which has appeared even in the cover page, where the yarns will have different properties. For example, it is functional properties, its aesthetics, and its life cycle. Life cycle is applicable to everything, even though we don't do it. In the case of functional and for electrochemical things like energy storage and energy conversion, we need to characterize its electrochemical properties, like specific capacity, charge conversion efficiencies, energy and power densities, cycling stability. A lot of these electrochemical parameters are to be evaluated. Next is non-electrochemical parameters, like you have a yarn and you are developing into a cloth. How is it going to perform in your cloth, for example? Your cloth will be washed several times. How it can sustain the mechanical torture during washing, stretching, or stitching, all those things. So we need to characterize in those terms also that they are non-electrochemical based characterization, for example, flexibility, torsion, stretchability, and aftercare properties such as washability and dry cleaning, strength, all those things are to be characterized. Next one is, it is not like, suppose you have in your mobile phone a silicon crystal there, you don't worry about its aesthetics. How does your silicon crystal look like? You are not worried about it. You no longer care about it, how the crystal look like. But that's not the case when you develop a cloth, electronic cloth, or a smart clothes, and you need to wear it outside. How is aesthetic is? How can its handleability, handleness, color, appearance, comfort? Who wants to wear a cloth weighing 50 kilograms? It's not going to sell out. So these are the things which also to be included when we develop a fiber cloth. Next issue become really one of the important issues in the modern world is life cycle. There was a recent statistic saying that we double the waste production, we means human being, double the waste production in 10 years time. We have seen, I was in Toronto, I was living in Toronto, we know the waste issue there. And I left 10 years ago, so most likely it would have doubled because the population is increasing. So the waste is a serious issue. And if our cloth is going to be dumped the way we dump plastics, it's going to have another environmental threat. So how do we recycle them? And what is the life cycle of your clothes? How many years it can live, or it lives only months or weeks or days? Then you need to characterize its life cycle too. And most of the conventional routine experiments in the universities, we don't care about its life cycle. We leave it for somebody else. But we need to change that attitude, and right from the beginning of materials development, we have to be careful about our life cycle, the life cycle of a product. I will brief a few examples before I stop. I think I'm getting out on time. So this is an example for how do we develop piezoelectric nanofabrics. This work was done in collaboration with Amir Kabir University of Technology in Tehran. We have a memorandum of understanding with them on this Electrospun clothes and devices. So this work is done in collaboration with them. We'll see that piezoelectricity is simple when we apply mechanical pressure or mechanical force. Some material has the ability to generate electricity. In case of polymers, PVDF, polyvinylidene fluoride, it has that property. When a mechanical force is applied, it generates electricity. There are numerous inorganic materials with much better piezoelectric coefficients. So when you look into some daily aspects, for example, when you walk, it creates about 67 watts of energy. And when it is converted into electrical energy equivalent, it is about 18.9 joules. And from your blood flow alone, it is continuously flowing. We don't realize it. Even it can generate about nearly 1 watt of energy, mechanical energy, and it can be converted into electrical energy. So there are plenty of avenues in the daily life. We can see that a mechanical pressure is applied. For example, when you walk, if you develop a piezoelectric clothes in your in the bottom part of your shoes, On your each step, you generate electricity, and if it is connected with a battery, you can store all those electricity charges there and can be used to power many of your electronic gadgets. So, in the case of piezoelectric polymers, this is the most famous one, polyvinylidene fluoride, and it's copolymer with trifluoroethylene. This one PVDF has many polymorphs, actually 5 polymorphs, alpha, beta, gamma, delta, and epsilon phases. Among them, dipoles in the alpha and epsilon phases are stacked anti-parallel, what I shown here in the left image. The dipoles are stacked anti-parallel, so that is non-polar. On the other hand, materials like the phases like beta, gamma, and delta, the dipoles in this one are stacked parallelly and show ferroelectric and piezoelectric properties. So if we can develop a beta phase of polyvinylidene fluoride, PVDF, and its copolymer, we can have good piezoelectric clothes for our daily use. There are many ways the piezoelectricity can be characterized. Is written here. I will leave this presentation, and those who are interested can read it later. Electrospinning is typically a good method, good process for developing piezoelectric clothes, because in electrospinning, we develop the fibers by electrically stretching the fiber, the polymeric jets. Means even in the beginning, the electric field is applied in this jet, so that conventionally all these piezoelectric materials is to be to undergo poling to increase the dipole alignment, means aligning the dipoles. But that's not really required in the case of electrospinning, because it's already under high electric fields, so it's already poled. The next thing is that by controlling the electrospinning parameters, you can actually control the dimensions of a fiber. About more than 10 years ago, when I was working in Singapore, we have proved that electrospun fibers containing very small diameters has already higher strain. So the materials, the narrower, the thinner fibers that we can create, the higher strain it has. When it has an intrinsic strain, it will offer you much higher piezoelectric coefficient. In this particular case, like what I shown before, we have developed two sets of polymers, PVDF fibers, PVDF and its copolymer. One is aligned. Aligning is by means of controlling its fiber direction using two rings. The details are there in this publication. And we get the fiber bundle. That fiber bundle is twisted to get yarns, and then those yarns were plied to get more strong yarns. And finally, these yarns were woven to get a cloth. Is that there is a comparison given here. In the case of random fibers, there is still significant fraction of this, over 50% of the phase present in the random fiber, where the fibers are randomly oriented in your fiber clothes, It's about 53% in the case of random. But when it is further aligned by means of electric fields, it again get better poles and got about 67% fraction is beta phase. And when we make yarns, we further applied mechanical stress in it. That's one is which we have beta phases of about 92% beta phase, means almost complete fraction of this PVDF yarn is beta phase. I think that is one of the best results so far achieved. And this one, we have systematically investigated the effect of different things. For example, the effect of yarn linear density or TEX, people from textile engineering background, they know this parameter text. The number of fibers in your yarn, and how the number of fibers in your yarn changes the piezoelectric coefficients, and how the twist parameter, the number of twists changes your piezoelectric parameter coefficients, and effect of plying, how many means you took 2 yarns and applied together to make a single yarn, or 3 yarns to make were plied together to make a single yarn, and so on. So what is the effect of plying on piezoelectric coefficients? And what is the effect of fabrics? For example, when they are woven into a piezoelectric fabric using weft and warp. Here we used copper wire, very thin copper wire, about 30 micron thick copper wire as the weft electrodes, and these piezo yarns are the weft electrons. We have developed this textiles here. That's what you are seeing here, and systematically investigated what are their effects. The results are summarized in this table, in this slide. We have shown that the best number of fibers in a yarn is about 40. More than that, we get lower piezoelectric voltage. And twist, we find that about 3,000 twist is good for getting better piezoelectric coefficients. Plying, we find that 3 plying is better than 2 plying and single plying. And effect of weft and warp density, we find that when there is about 20 weft and warp, then we get the best piezoelectric coefficients. So those are the conventional results we got it. And some results I want to convey, and probably a lot of things to investigate, probably using Raman spectroscopy too, is the final piezoelectric voltage that you can obtain. Here, when you look at this slide, this is the effect of polymer. From the geometrical parameters, we isolated the best piezoelectric condition, and then developed a fiber of this PVDF with its copolymer. You would see that we can have piezoelectric voltage up to over 2000 millivolt, means more than 2000 volts. Sorry, more than 2 volts is possible from a single fiber of about 300 micron thickness, diameter, and 5.5 centimeter long. We can have that kind of voltage from this piezoelectric yarn. But what is disappointing is when you look into the right-hand axis, where the power is noted, even with a volt scale, potential of volt scale, the power we are getting is nanowatts. Means that the current through this material is pretty poor because of the inferior current conduction mechanism in polymers. So how do we develop this for piezoelectric polymers with better conducting properties? What is the best strategy to improve this conductivity, and what different spectroscopies can help us in finding the targeted devices, target structures is still ongoing, and that's where brilliant brains are required. Finally, let me brief some of my activities on perovskite solar cells too. Perovskite solar cells were discovered about 10 years ago as a relief for the photovoltaic community working on the 3rd generation solar cells. How do we rate, or how do we rate the goodness of an ideal solar cell, or how do we define an ideal solar cell? We tried to do this in an article published in Energy and Environmental Science in 2014. written by us and some of our European counterparts. We define that an ideal solar cell should have 4 qualities. The efficiency is the first one, cost is the next one, stability, how long it can work is the next property, flexibility, like functionality, like transparency, flexibility, color, aesthetics, and easy integrability to other structures is the 4th functionality. If a solar cell can have all these properties, it is the ideal solar cell. You can easily see that most of the established technologies, the 1st and 2nd generation solar cells, for example, silicon and thin film solar cells, they offer all these three things, like efficiency, cost, and stability. The cost of silicon solar cell is not, or the blame should not go for the silicon solar cell. The blame should go for the battery side and their wiring. Silicon solar cell is pretty innocent in that case because the cost is pretty small. Stability, but silicon is an inorganic device. It cannot be. It cannot offer the band gap is 1.1 in the IR side, so it cannot be transparent. So and since it is an inorganic one, it cannot be flexible. And it is, since it cannot be transparent, it adds no aesthetics to your devices. It all looks a similar thing. That's where this 3rd generation solar cells coming in. 3rd generation solar cells, or in general called organic solar cell, they offer this, the functionality. They can be transparent, flexible, it could be colored, and it can be developed in multiple color even, and can be easily integrated into your clothes and utensils. But there are other issues which is summarized in this one. For example, if we divide this 3rd generation solar cell before and after perovskite solar cell. Before perovskite solar cell, it was dye-sensitized solar cells and organic or bulk heterojunction polymeric solar cells. Their efficiency is poor, stability is poor. But when it comes to the perovskite solar cells, 3rd generation solar cells after this one, there were 2 red side for dye-sensitized solar cells and organic solar cells. Both efficiency and stability were low. But when it goes to perovskite solar cells, we could eliminate one of its drawback. Efficiency is pretty high, and efficiency can be as high as that of silicon solar cells. This is a slide where summarize the development. You can see that the sharp rise in efficiency. This is a table I took from everybody. Search with Google can get this information from this an NRL chart published periodically. You would see that the rising of perovskite solar cell efficiency. Currently, it has about 25.2% certified efficiency. And what makes us really proud is we were the first to build a perovskite nano road solar module. I have briefed you before, for which we were given a lot of recognition. And from there, we not only developed this one, we addressed few issues of stability also, which is given in this slide. The stability of perovskite solar cell is one of the biggest issues, or the biggest issue in, not one of the, it is the biggest issue in perovskite solar cells. There are many theories and experimental evidences what makes the perovskite solar cell unstable. One of them is its intrinsic instability, because perovskite, even if it is not inorganic perovskite, it is an organic, inorganic hybrid perovskite. The organic part, in most cases, it is a methyl ammonium halide. When you look into the symmetry and the geometry of that molecule, you will see that that's a polar molecule. And when you look into the geometry of this perovskite crystal, you would see that the what is that? The octahedra in perovskite, methyl ammonium halide perovskite is tilted. Means there is an electric field due to the octahedral twist in perovskite, and you have a polar entity at the middle of the perovskite, at the S side of this perovskite lattice. So there are two competing electric fields. So when there are two competing forces, how can it be stable? So that there is an instability, intrinsic instability, because of the mobility associated with this methyl ammonium ion. And from our nano road solar module, we have shown that is probably there is ion migration between the electron transport layer from where the or to where the electrons are injected to from perovskites. And we have shown that when we use very highly crystalline nano rods, that is microscopically much bigger, means dimensionally much bigger than corresponding nanoparticle. Our nano rods is about 100, 200 nanometer wide and about few micron thick. So that's, we can consider it as a bulk material. And most of them were single crystals. And when we have that single crystal electron transport layer, and when we compare this, the efficiency of the variation of efficiency with the time of the perovskite made in single crystalline perovskite and nanocrystalline perovskite, you will see that nanocrystalline perovskite decays very fast. So that's one thing associated with crystallinity. And there is another theory published from Okinawa Institute of Technology. And what they find is that it is the iodide ions in the perovskite lattice is not really stable. It can be well imagined when you have, when your perovskite, when your methyl ammonium halide ion is displaced, your crystal is getting electrically charged for the neutrality. It removes some iodine. And because since this one is continuously moving, iodine is continuously removed from the perovskite lattice, eventually it goes to it goes to be destabilized. One another thing that we have tested is what happens when we encapsulate the perovskite in a polymeric matrix. We have shown that when we encapsulate the perovskite in a polymeric matrix, we can actually enhance the stability. You will see this this blue one, the absorbance. It is really stable even after 2000 hours under normal conditions. So those were the results where we further developed to make a yarn, perovskite solar yarn, which we recently published in Rapid Research Letters of Wiley. And that was even chosen for a hot article on solar cell technology, where this work is done in collaboration with Shanghai, Donghua University in Shanghai, where we have developed a yarn. The yarn is not really simple. The structure is not really simple, but the perovskite what we used is a methyl ammonium halide perovskites dispersed in a polymeric medium. And when we do that, we not only get, let me skip it, I think I'm running out of time. When we do this, you can see this is the black curve is the uncoated device, and uncoated means unpolymerized or not dispersed in polymer. You will see that the PC power conversion efficiency rapidly drops to 0. But that's not the case when the perovskite is included in a polymeric matrix. It is pretty stable. It's stable, and it can, for a fiber of about, we could develop this fiber into large scale. What you see here is actually a perovskite fiber bundle created using this technology, this methodology. There's some of their images, microscopic and macroscopic images, photos and microscopes. And we have nearly 2 volts from this fiber of about 5.5 centimeter long and about 300 micron thick. And when we made several twists, we did so many experiments. The details are actually there in that publication, Solar RL. You can refer them. We have efficiency as high as 15.7 in yarns. But again, when it goes to a fabric, where we made a fabric using an electron absorber and electron conducting medium as the warp electrodes and carbon yarn and a hole conductor along the weft electrode, the power what we get is pretty small, like 1.6 milliwatt per meter square, and that's because its current is poor. It's probably because of this architecture. There could be so many short circuits, but even with that, the short circuit, it can be easily seen from the fill factor. See, the fill factor is pretty lower, less than 1, whereas the fill factor of the best device is about 54, about how many, 100 times better. That's why the difference in power is coming in. So still, there is numerous things to be done in this case, which and it has to be developed into a deployable device. Still, it is not. The research is still going on, and very recently we have made a knitted solar fabric. So to conclude, there are plenty of issues in textile electronics. Enhancing the properties of polymers is one of the biggest issues, especially in increasing the electrical conductivity, where people from different areas have to come together and work together. People from chemistry, materials, and physics background, they need to work together to solve these issues. The next one is recycling. When we have this kind of enormous amount of electronic clothes dumped without recycling, without recyclability, that's a major issue. We have written an article recently with the title that if we engage artificial intelligence, then the circular economy means taking back all the essential components from a used product back into operation, back into production. If you engage artificial intelligence in circular economy, unfortunately, I'm sorry I didn't give the details of that paper here, is probably can solve a big issue of recycling. Still, the industrial scale fabrication of functional lamps is a big issue, and cost per unit performance has to be optimized to send it for production. Product lifetime, some polymers are good, some are bad, and how do we tailor, engineer the life cycle of those products are still big issues in textile electronics to see its full potential. And finally, this is my team. Some is only the bottom panel of these figures are the people currently in the lab. All others are left and working somewhere. Thank you for the attention again. If you have questions, I'm happy to answer. Thank you very much.